microfono. Sì. Prova. Sì, ecco, troppo carico. Un attimo. Allora. Un po' meno bassi. Tac. Sì, prova. Si sente bene. Bisogna che vai a provare su una macchina. Vabbè.
Per vedere com'è il
Sì. Prova. 1, 2, 3, prova. Aumentiamo un pelino. Ci siamo. Stai provando da lì? Dimmi quando devo parlare che così mi sente. Sì, prova. Se ti parlo tu dovresti sentire. Ok? Va bene. Ascoltami, voi fate fino a 1. Adesso siamo vicini io e te. Fate fino a 1.
Sì, ma lo guardo qui. No, cambia un po'.
Sono andato poi poco, adesso ancora di più.
Sì.
Ok, dagli un attimo.
Ancora un pelo in basso verso come stai andando. Ancora un po'. Ecco, ancora un pelo. Vai. Ma ecco, adesso la scritta è buona. Questa qua sì, quella un po' meno. Va bene così? Prova a abbassare un altro po'. Dovrebbe essere più vicino alla videocamera.
Però se zoom un po', dopo
No, non si perde tutto.
Siamo
Sì, va bene così secondo me.
Barbara? Allora aspetta, diceva di più prima. Ciao. Che parte
Sì, sì.
Allora, aspetta, adesso devi spostarti un pelo in là.
Forse è questo.
Ah sì, può
funziona
essere
il
che
mute.
fischia per la scala.
Funziona il mute e quindi l'ho tolto.
O facciamo così e te lo accendo quando parli.
Aspetta, vado, mi sposto io. No, non mi sposto.
È acceso, vero? Prova. 1, 2, 3, prova. Non sembra acceso. Okay, so let's start. For those who just arrived here today and they are on streaming, welcome to Ferrara. So I've let me start just thanking the speakers for today, and particularly those who came not from very far, but like Giovanni Losurdo and Marco Di Pietri, who join us today for this workshop. So I don't have to convince you that this this event, August 17th, 2017, will be remembered like a watershed event in history of science. It's when the papers, more than 100 papers came out in September describing this event following the LIGO VIRGO paper. We thought here with Alessandro Drago and Cristiano Guidorsi that it would have been a good idea to have a mini workshop here to host this event here, because there's a good reason. I mean, there are two strong traditions here in this department who have to do a lot with this discovery, not with the discovery, but with the physics that is around the discovery. One has to do with basically the discovery of the afterglow of gamma ray burst that Filippo Frontera and his Beppo Subs team did now 20 years ago. And this has trained a generation of astronomers to refine the observational techniques to follow up these sort of events. And the other, there is the tradition that Alessandro Drago has been leading on studying nuclear physics with at the string densities with compact objects. And so we thought that this is one of these rare opportunities where we can have different physicists coming together, something that happens quite rarely these days. In fact, an opportunity to counteract a bit the fragmentation of science that we have today, because as we know, here there are different fields which come together for this discovery. And so today, so you have seen the plan. The plan is to have 4 talks. The 4 talks will cover the 4 cornerstones of the discovery. And so not only then we've seen obviously the discovery of the event, the gravitational wave detection. Then there will be another talk by Cristiano Guidorsi on all the physics that we can learn from studying from the electromagnetic afterglow of the event. Then there will be another one describing the modeling. It has to do with strong gravity. Then the modeling of neutron star mergers, and another one by Alessandro on nuclear and hadronic physics. So before I invite Giovanni Losurdo here on stage, I would like to thank ENFN and Lele, who I don't see here, but Lele Tripiccione, who has made this event possible. And then I will invite Giovanni here. Giovanni Losurdo has been leading, in fact, the development of advanced VIRGO over the last years. He has been involved in VIRGO, I think, from the days of the thesis. And so on August 1st, he delivered, in fact, the experiment to the VIRGO team in Pisa, or near Pisa. And I think this was when his job, in a way, ended. So I don't know whether he will tell us whether he anticipated on August 1st that August would have been such a hot month. But indeed it was. And so I invite Giovanni here on stage to give the first talk for this mini workshop.
Thank you, Piero. Thank you for the invitation. And I would like to start this talk by remembering Adalberto Giazzotto, who passed away just 1 week ago. And he used to say when we were students, detecting gravitational waves, no idea is crazier than this. And now we can turn this sentence in the past tense, because finally these have been detected. And great merit goes to the vision and the pragmatism and the scientific toughness of a scientist like him. Also because realizing this enterprise in Italy doubles the difficulties because of resources, because of bureaucracy, because of an enormous amount of additional challenges that he had to find and tackle. So, gravitational waves have been detected. This happened about 2 years ago, 100 years after the Einstein prediction. And this happened with an event which was absolutely astonishing in terms of beauty. Let me call it beauty. Because basically you can see the signal clearly visible in the data, and because the waveform was so clear that everybody thought at the beginning it was the post-Newtonian formalism, and what you can expect from numerical relativity. The two predictions matched beautifully, and again, this was not obvious at all. We learned a number of lessons. It was the first direct detection of gravitational waves. It was the first direct observation of black holes. It was the first observation of the larger known stellar mass black hole, larger than 25 solar masses. First observation of binary black hole system, first observation of binary black hole merger, and first test of general relativity in strong field condition. There was one more lesson, this is my experimentalist point of view, was that ground-based interferometers had finally demonstrated to be the right instruments after decades of development. Then let me jump to, there were more detections of similar events by the two LIGO systems. And then on August 1st, VIRGO joined the observation run named O2. And it was the first time that three two-generation detectors were online together, acting as a single machine. I would like to remark these two words. Single machine was an expression invented by Adalberto Giazzotto in 2001, in a moment where LIGO and VIRGO were still acting as competing projects. And he went on stage in one of the Amaldi conferences, said, we need to realize a single machine, which does not mean simply running three detectors in coincidence. It's something more. It means that you treat the three data stream of the three detector as a single vector, and you do the analysis on this vector. And in this way, you can in several occasions, you can enhance the signal-to-noise ratio, and you can detect signals that on single detectors you are not able to see. And so finally, this is the signal machine. Is a quite wide triangle. Unfortunately, all the detectors that we have and that we are planning to have are in the northern hemisphere. And having a detector in the southern hemisphere will be very much beneficial for the angular accuracy of our measurements. So we have the two LIGOs and VIRGO here, and we will soon have a Japanese detector, Kagra, which is currently in construction, and the LIGO India in 2024, 2025. This has allowed to prepare with a few years in advance a larger network for the electromagnetic follow-up. And currently there are 93 groups managing over 200 instruments, which have signed a memorandum of understanding with the LIGO-VIRGO collaboration for the follow-up. I believe that this is a very crucial step towards better science. This was not obvious at all, because, and there are also sociological reasons for this, because while LIGO and Virgo collaboration have been started by people coming from a high energy physics background, and so people were used to large collaborations, large international collaboration. Astronomers are more used to smaller groups, often in strong competition, and that's why it's not always easy to make them collaborate and convince them to write a single paper. But I think that thanks to the latest events, a lot of progress have been achieved also on this front. So the O2 run had started earlier. In fact, it had started in November 30, and from the beginning it was known that it would have stopped at the end of August because. Okay, because sorry, because LIGO had already planned a major intervention on the vehicle system, which could not be postponed. So Advanced Virgo had started all the project 2 years later. Been founded 2 years later, started the construction 2 years later. So it was in a rush to join this O2 run before the shutdown. And finally, we managed to achieve this goal on August 1st. From August 1st to August 25th, there were about 15 days of triple coincidence observation. And previously, there had been one black hole event published on January. So finally we had a network of 3 detectors. Virgo joined with a worse sensitivity with respect to 2 LIGOs basically because we had just 2 or 3 months to work on the sensitivity improvement. And the situation was that we had 1 LIGO with a sensitivity with the capability of seeing binary neutron star as far as 100 megaparsec. The second LIGO at 50 megaparsec, and Virgo a bit below 30. So that was the situation. For what concerns Virgo, it is important to remark that, oh my God, the best. That's me. The black curve here is the best sensitivity curve that had been achieved by Virgo in 2011 after about 6 years of commissioning and improving the detector. And the red curve was the one with which Advanced Virgo joined the run after 3 months of commissioning. And you see that passing from red to black to red means enlarging the observed volume of universe by a factor 12. So it's a lot, and it's impressive that this was achieved only with a few months of work. This means that the detector is really an advanced detector, and also that the people who first ran Virgo are now much more expert in running this machine. Now let me go back to the O2 science. So on August 14th at 10:30 in the morning, there was the first detection of a transient gravitational wave signal produced in a collection of 2 stellar mass black holes. It was a highly significant event, a Foster run rate of better than 1 into 27,000 year. And this is it. It was detected by Hanford with signal to noise ratio of 7, by Livingston signal to noise ratio of about 15, and by Virgo 4.5. Clearly Virgo has a worse sensitivity, so the signal to noise ratio is less. But if you look if you compute the signal to noise ratio of the 3 detector networks, so once you consider the three detectors is a single machine. Signal to noise ratio is higher, it's about 18. So that's the added value of the network. And clearly for us, this plot is very important. It's a very emotional moment, the first event seen by VIRGO. Again, like I said, it was binary black hole coalescence, two black hole 30 and 25 solar masses, and again, like in the first detection event, about 3 solar masses went into gravitational waves. And this event adds to the previous ones, is showing that there is a population of black holes that is in some way complementary to the one that had been measured through X-ray studies, and this is food for brain for the astrophysicist. What is striking on this event is the localization, because for the first time it was possible to pass from over 1,000 square degrees localization area to 60 degrees squared. And also the third detector helps in reducing the uncertainty of the distance. So you see, this is the distance measured by the two LIGOs only. In the mind of everybody, this was more than enough for the first joint run of the three detectors. So we are ready for all of it. But there wasn't even the time to celebrate. Oh, there is something more that I want to say on this. First of all, this is for comparison the area identified by the first discovery of gravitational wave with the astronomical follow-up. Each of the green boxes of square is an observation run by one of the observatories, and you see that when the area is so big, you need really hundreds of observations to cover it all, and basically means a lot of time of observation. There's another physical asset in this event. It's the first ever measure of some polarization feature of the wave. There was actually the analysis done to this extent has been just a provisional analysis which simplifies a bit the scenario. So in principle you can have 6 polarization states. The two tensorial one foreseen by the general relativity, the so-called H plus and H cross, the scalar graviton, spin 0, and 3 vectorial polarization states. In principle, you can have a polarization which is a combination of 6 states, while in this analysis we only considered pure tensorial, pure scalar, pure vectorial polarization states. And the result of the analysis is that the general relativity, so purely tensor, is favored by 200 and 1,000 times with respect to purely vector, purely scalar polarization. Analysis is not complete, but conveys already the message of the amount of information that one could, in principle, find out from these events. So, in summary, this was the first event seen by VIRGO, the first event with a small sky localization area, enabling efficient multi-messenger observation, and the first event allowing polarization studies. But like I was saying, there was not even the time to celebrate that 3 days later we found it. And that is it. It's a fantastic binary neutron star in spiral merging. You see the interesting feature here is that was clearly visible in the 2 LIGO detectors, and unexpectedly, because this is a very high signal to noise ratio event, it's hardly visible in the VIRGO signal, in the VIRGO data stream. And the reason of this is that these detectors have an antenna pattern, are roughly isotopic, but they have blind spots. They have a lobed antenna pattern, And in fact, when you say that a detector has an spiral range of 28 megaparsec for binary neutron star, this is an average number. It's average over polarization and over sky location. And in fact, it means, namely, that this range, sight distance ranges between 63 megaparsec, which is the point of maximum sensitivity, and 0, which is the sensitivity in the blind spot. And there are basically 4 blind spots, 1, 2, 3, and 4, over the interferometer plane. And so the reason why VIRGO was not clearly seeing the signal is that it is very close to a blind spot. And paradoxically, in a sense, this helped a lot to improve the localization. But this is not all. The 1.7 seconds after, there was a short gamma ray burst event detected by Fermi and Integral, independently detector. And I think that this figure here will go in the textbooks, because it's the first time ever that there is a clear experimental correlation established between the BNS and the short gamma ray burst, which was assumed earlier in theoretical works. The localization of the event was very accurate, 31 degrees squared, and with the online analysis, and a bit better with the refined analysis. And the initial alert was given to the partners 27 minutes after the detection. And this led to a lot of studies, and eventually in a paper signed by over 3,000 people, including LIGO, VIRGO, and the follow-up partners, which marks the start of the gravitation of the multi-messenger astronomy using gravitational wave. I will not say multi-messenger astronomy at all, because we should never forget the work already done on the supernova 1987A with the neutrinos. So, in the summary, we saw that there was a spiral emerge of BNS. The two neutron stars merged at speed of about 1/3 of c, leading to gamma burst. The ejected neutron-rich material was decays to heavy elements, and this was observed as a kilonova. And then there were also the X-ray and radio afterglows detected, formed by bubble of ejected material expanding into the surrounding interstellar medium. Some more details on the gravitational wave signal. The network signal-to-noise ratio was above 30, so it was the loudest signal so far, even louder than the first detection. But what's really striking is the duration, because this event stays in band for about 100 seconds, so thousands of cycles, which really permit to do some accurate analysis. And accurate analysis means that you can measure the chirp mass with an error which is very, very small. This does not reflect directly into the measure of the single masses, because there are other parameters in the theoretical form of the signals which spoil the accuracy, and the luminosity distance was about 40 megaparsec. Eventually, this is the shortest, the closest gamma ray burst ever observed. Now, I don't want to tell something about neutron star, because this will be a topic of the forthcoming talk. I just want to show how these impacts on the experimental effort that we have to do. So we know very little on how a neutron star is made. But we know that we can in some way have a hints on the neutron star structure if we measure the equation of states. But there are many models of possible equation of states. In the end, we can simplify the picture by distinguishing more compact, so stiffer equation of state for more compact stars with smaller radius or less compact stars. And from the, in the end, this relies with the type of gravitational wave that the star is emitting in the merger phase. So each of the two neutron stars is subject to the tidal field of the companion star, and this tidal field couples, induces an additional quadrupole moment in the companion star according to a function which depends on the mass and on the equation of state. And then the time varying quadrupole moment leads to emission of gravity waves. So in the end, we start with a spiral wave that is the same in all cases, but when the star gets closer, you have the equation of states, and so how much the stars wants to be deformed has an impact on the waveform. And if we compare these predictions with what we see in the detector, we see that there is eventually an impact in the high frequency part of the waveform. So the better the signal, the better the sensitivity and the frequency, the better the capability of the detector to discriminate between different models. What we could do with this event was to make general considerations which exclude radius larger than 14 kilometers. This is not much, but it is a beginning, and is a clear indication that we need to improve the detector further, because there is a lot of interesting physics to be done there. Moreover, these events are standard sirens, so basically in principle we can have an independent measurement of the Hubble parameter, which doesn't make use of the cosmic distance ladder. In fact, things are a bit more complicated, because the amplitude of the signal which we measure depends on the luminosity distance, but also on the inclination angle of the source, which introduces the additional degeneracy. And this is the reason why in this event we could give a measurement of H0, but still with an accuracy that is too large to become able to say which one of the previous measurement intention, the one from Planck and the one we choose is the most likely. So, but again, in this case, for instance, we've been unlucky because VIRGO saw a very small signal. Had VIRGO seen a signal with larger signal to noise ratio, we could have been able to improve the discrimination between the two polarization states, and so improve also our capability to measure both the inclination and the luminosity distance. So again, food for the next rounds. By improving the signal to noise ratio of this detector, we will be able progressively to improve this measurement, and so to tell something also about cosmology. Moreover, fundamental physics, speed of gravity. The gamma burst and the gravitational wave arrived with a delay of about less than 2 seconds over a trip of 130 million years, which is absolutely remarkable. And you can easily constrain the speed of gravity, and you get and you find a result that gravity travels at the speed of light with an accuracy of a part on 10 to the 15. And then there was what you know better than me. Many people in this room know much better than me. So the follow-up of the evolution of the spectra measured in the optical counterpart, which led to the evidence of formation of chemical elements heavier than iron, and which was certainly a remarkable discovery. So this event was another spectacular discovery in a new era of astronomy, and then astrophysics, cosmology, nuclear physics, fundamental physics, but in the end I will say physics. And it's likely to be just a preview of what can come in the future from the observation of gravitational wave and electromagnetic and particle follow-up. It's when you get to this such an important result, it's important to look back. And I found this sentence in the VIRGO proposal, which was submitted in 1989. In the introduction written by Brier Jazot, it was written, "VIRGO must be considered both as an experiment and as a step towards a future observatory. It has the long-term goal of being one component of the gravitational wave detectors network." And then it talks of the effort needed to generate the international effort required by the birth of gravitational astronomy. Now, these sentences sound very obvious now, but 30 years ago, in a moment when everybody was skeptical in the possibility to detect gravitational wave, when the attempts that were being done in Europe and the US were based on strong competition, and basically everybody all wanted to do the job by itself. This is indeed very, very prophetic. It shows an incredible vision, which is a fundamental ingredient to make science progress. I think I told already too much. Let me just tell a couple of more things. Another important lesson on the experimental front is that we should not forget the number of events that we can see is proportional to the sensitivity cubed, so the cube of the distance at which the detector can see times the observation time. So it's good to observe for a long time, but it's even better to improve the sensitivity further. This is the reason why LIGO and VIRGO stopped the observation to work on the detector. And so the perspectives now are the following. We have in VIRGO we have already increased by an order of magnitude the volume of universe that we can observe with respect to the best VIRGO. And now the goal for the next run, which will start in fall 2018, is to gain another factor 10 in volume. Next fall, there will be a new run which is expected to last at least 6 to 8 months, with both LIGO and VIRGO which have improved their sensitivity. And then in 2020 we should have also CAGRA joining the network, and then later LIGO India. And in the end, in a few years from now, we will have a network of 5 detectors which will be able, in principle, to detect more than 60% of the sources, to localize more than 60% of the sources within 10 degrees square, which will be a remarkable progress. And then in the long term, there is the plan to realize a 3rd generation detector, which in principle should be able to detect recoalescence of binary black holes at a redshift of 20 or even larger. So this will be really the instruments which will be able to do the cosmology. And I would like to end with a sentence from the Siderius Nuncius of Galileo, which impressed me. Grandi invero sono le cose che in questo breve trattato io propongo alla visione e alla contemplazione degli studiosi della natura. Grandi dico sia per l'eccellenza della materia per se stessa, sia per la novità loro non mai udita in tutti i tempi trascorsi, sia anche per lo strumento in virtù del quale quelle cose medesime si sono rese manifeste in senso nostro. And I'm very impressed by how much these sentences could perfectly be the introduction of the paper which have been published after the August event. And I thank you for your attention.
Grazie. Thanks, Giovanni, for this great introduction. So, you know, the point of this event is this is a workshop, so anyone should feel at ease with asking any kind of question. So it's an informal part, a very important part of this workshop. So please, well, okay.
I think there was a little misprint probably in one of the last slides, because if you put a limit on the radius, telling that the radius has to be smaller than something, that essentially means that the gravitational state is softer, not stiffer.
Oh, maybe thank you for spotting that.
Yeah, it's there. Data favors stiff, data favors soft.
Oh, yes, indeed, absolutely. Absolutely.
Okay, Guido.
Giovanni, you had VIRGO running for about 1 month, a bit less, and you had 2 events. Now you're going to be increasing the volume of detection by factor 10. You're going to be flooded by events, I think. So, and even Einstein telescope in the future will have just an incredible number of events. How are you going to cope with this?
Indeed, we don't know, because we were not expecting this to happen so soon. But it's a clear challenge. It is a computing challenge. It is a data analysis challenge. And if you think that, for instance, a few days ago, we have published another binary black hole detection, which was indeed recorded in June. And this, why? Because people had not time to do all the analysis after the August events, which were clearly more important and more urgent to publish. And so already now we are let's say, not able to follow up all the data which are coming from, which are being produced by the detectors. And so clearly these require a change of scale in the effort, but there are other communities who are already doing this. For instance, the number of data analyzed at SREN are much larger than our. And so clearly there is one of the challenge we have to tackle is to grow as collaboration. We need more people dedicated to modeling, producing waveforms, doing the analysis, working with the computing, finding strategies to make the computing faster. So we certainly need to grow. Our community has started mostly as an experimentalist community, but now we need to recover on that front. Otherwise we will be overwhelmed and we will be forced to discard events.
Okay. So, let me ask you, with the advanced LIGO and VIRGO, what will be the expected angular resolution for positioning of the binary neutron star merging, and there will be a smaller resolution for the angular range of positioning?
Yeah, okay. So first of all, let me say that the resolution you get depends on the position of the source of the sky, of the source in the sky. So For some location, you get a few tens degrees. For some location, you get hundreds or 200 degrees squared. Then it also depends on how strong is the signal. And so you expect some improvements in the resolution as far as the sensitivity gets better. But let me say that the ultimate target you can expect is the 10 degrees squared that you can achieve when LIGO and VIRGO will be at the design sensitivity in some regions of the sky. When also LIGO India and CAGRA, so when you will have 5 detectors running together, so you have a better coverage of the sky, then you can expect to be at the level of 10 degrees squared for most of the sources that you see. That's, I think, the best you can do with the second generation detector. Then I see Julia, maybe she wants to add something to this. Well, for the next target, that could be the 1 degree squared, you probably need to have third generation detectors in several locations of the world.
Just a question. I was surprised to see that the significance of the signal in VIRGO is now recognized to be 4.2, 4.4. But at the beginning, the result published also was 2 sigma.
Well, okay, let me say something.
And also was discussed in several workshops.
It was a bit more than 2 sigma, but let me say something that rather than, in fact, the main point is this. Had this been a single detector detection, this would have been discarded because it's a sub-threshold detectors. Our threshold for claiming a signal, if we're claiming a detection, is a signal to noise ratio of 8. So in this very case, even sorry, I've gone too fast. Even LIGO Hanford was a sub-threshold, but that's the value of the network.
In that case, you see some evidence.
No, but you see, or now the screen is not so clear, but you see the evidence also here. The point is that you have, it's not the eye which
decides. It's the first time I see this figure.
It's the first time you see this.
Yes, because
the previous event, this is the black hole, black hole.
Yeah,
no, sorry.
This is the black hole, black hole.
This is there was this event a few days ago.
Okay, now you are okay.
Not the 1708.
This is it. You are talking of this one.
Yes.
Okay.
Yes,
no,
sorry.
in this case, what you expect, taking the LIGO signal and considering the antenna pattern, you expect to see a signal in VIRGO with signal to noise ratio of about 2.4. Okay. And the data are compatible with a signal to noise ratio of 2.4. But you cannot say whether this is a signal or basically you don't see the signal. Basically you don't see the signal, yes.
And then, however, in spite you don't see the signal, you give an information important.
Which is crucial.
Crucial.
Yes.
But I don't understand how you have given.
Okay.
You have to explain the bit of the blind spot.
Decrease the error box.
Okay, so the reason is this. LIGO, the two LIGOs, let me simplify the picture. The two LIGOs can say, they see the signal very clearly. So they can say that the source will be in a ring, almost a ring, which is basically identified by these two blue bananas, okay? Yes. Then, for instance, if the source is here, then VIRGO should see it with a signal to noise ratio of 10, for instance. If it's here, VIRGO should see it with a signal to noise ratio of 9. And you do this game, okay, And you come to the conclusion that the only region which is compatible with the VIRGO data is narrowed to this green small banana. And the reason of this is that basically that LIGO ring spans through this antenna pattern, and you break the degeneracy of the LIGO measurement thanks to this blind spot here. So in the end, the only picture compatible with the data of the 3 detectors is that the source, which LIGO says can stay in one of the points here, is in fact here. And now, I know that if we had not found the optical counterpart, people would have been skeptical on this analysis. But the fact that in the end, the counterpart was exactly in the point in the small area indicated by LIGO and VIRGO says that the coherence of the analysis is confirmed by the experimental data.
Okay, so this is a point that I have not fully appreciated. So if VIRGO actually had detected, say, a phi sigma, the event, you're saying that probably the error bar would have been larger because you're in a region where the sensitivity doesn't depend so strongly from the geometry of the event. I mean, so, because at the end, the localization came from the fact that you didn't see the signal. You didn't see the signal bright enough.
This helped. Well, the localization was helped by the fact that the source is in a point where the gradient of the sensitivity is very steep. And this was an help. Now, what happened? What would have happened if we had seen the signal with higher signal to noise ratio? Depends on the position of the source. It could have been worse or better. I don't know. It depends from point to point.
Okay, Stefano.
When also the LIGO India and Kaga will be running, is it foreseen to have periods of running where you have at least 3 detectors working, operating, and maybe the other 2 in maintenance, in order to cover as much as possible the duty cycle?
Let me say, this has not been discussed mainly because of the fact that, for instance, there is no formal agreement yet with the Japanese detector. So it's not yet formally part of the network, but this is unavoidable. So it's unavoidable that we go in a regime where we exploit the 5 detector constellation in order to cover as much as possible not only the sky but also the time. It's unavoidable, yeah.
If I may, another question. You mentioned that the alarm was given in 27 minutes after the event.
The first alert, yes.
The first alert. But then the data about the gamma ray burst was immediate.
Yeah,
so
the notice of the gamma burst was immediate, and clearly these alerts are public, so everybody knew. But what happened was that when also the notice of the gravitational wave event was out, that was the moment where the excitation exploded in the world, because gamma burst was one of the many gamma bursts. But when was the news, okay, there is also a gravity wave event and the signal is compatible with the BNS event, and then people got crazy.
Which is the status of Einstein telescope? I mean, it's just a project of a piece of paper?
Okay, so it's an interesting question. Einstein telescope has produced a conceptual design.
and has produced a community which has gathered around this concept, which is larger than VIRGO, because this time the Germans and the British are in this project. At the same time, there has been an acceleration in the US for producing a third generation detector, which was not the case in the past years. And NSF is pushing a lot for having a collaborative effort. So we have just created joint groups to study the R&D to be done, the detector design, and the governance of a global effort for the third generation. And that's it at the moment. The missing part is about the possibility of being funded, because this detector will cost more than 1 billion. So it's an order of magnitude with respect to the current detectors. And on this side, I think that the August story, the entire August story, will certainly increase the chance for this detector to be funded. So now I'm starting to believe that in the end this will be done.
Yeah, so for doing nuclear physics, it would be interesting to have some, let's say, higher sensitivity, higher frequencies.
Sure.
So is there any way to somehow tune the sensitivity of the instruments to spoil maybe the low frequency part and to improve more on the kilohertz region?
Yes, these detectors have such possibility because we have a so-called signal recycling cavity. So there is at the output of the detector, where in the port where the signal is basically detected, there is an optical cavity which can be tuned, and depending on the tuning of this optical cavity, you can enhance the sensitivity in a well-defined frequency region, say 100 Hz wide. And this was originally introduced exactly for the reason that you wanted to. The idea in that case was, okay, suppose that there is a millisecond pulsar that I want to study, so I want to have the flexibility to tune my detector at the frequency of that millisecond pulsar. This can clearly be done by tuning it at the frequency of the merging of the neutron star. I must say that at the moment this is not done because it's experimentally challenging, but it's a matter of dedicating time for commissioning this opportunity. So in the future, it's certainly a possibility to be exploited. But let me also say that there is a lot of effort to improve the overall high frequency sensitivity by introducing quantum optics techniques like squeezed state in these interferometers, which overall can improve the high frequency sensitivity without recurring to very high laser power, which has other drawbacks. So I believe that already in 03 you will see a significant improvement in that frequency band.
Just a curiosity about the Einstein telescope. Obviously, with the Einstein telescope, we have a much higher sensitivity. I don't know, a factor
10 times larger.
10 times, a factor 10. But in terms, so if the Einstein telescope observes an event only by Einstein telescope, which is the capability to localize this event?
Yes, again, we need a network. Einstein telescope by itself, it's not sufficient. We need a network. So we need again to redo what has been done for the first and second generation detectors. Have more 3G detectors around the world. But let me say also that we have there is something very relevant which have started. We have new instruments which open a new window in the universe. These have been declared many times in the previous decades, but basically people were skeptical. Now it is there, and so this clearly triggers a development of the detector and makes appealing for other countries to realize their own detector. So it's conceivable, it will not be surprising then in the next 2-3 decades there will be a larger number of third or fourth generation detectors around the world, which make a much better network.
Okay. I think we need to move to the next. Well, let's thank Giovanni again.
Thank you.
So the next talk will be by Cristiano Guidorsi, who will tell us about the afterglow. In fact, this event, you can also call it GRB 1708, 17A. Right?
Sì, l'avevo provato, già funzionava, solo che...
Cristiano says that somebody has another question to Giovanni. So I have a curiosity. Why is Livingstone so much better than the other LIGO detector?
Oh, it's a weird story because they had the same sensitivity. Then there was an earthquake because there is Mount Helena in Washington State. And after this earthquake, for a known reason, they were not able to recover the sensitivity.
So in principle...
In principle, they are the same. They used to be the same.
Any other questions from the students? Let's say PhD students, so they are less afraid. So, Giovanni, is there already someone doing archival science with the data? I mean, going back, you alluded to this when. So, is anyone who is actually looking at the data? I was wondering whether there is enough manpower to look at the data at the previous streams and to look at lower significant events. Are there people who are looking to them and more sophisticated? No. They're too busy.
Marginally.
Marginally, okay.
Marginally.
Vuoi provare con l'altro?
Non so, cioè... No, dovrebbe funzionare, cioè, perché il MV...
Di metterla sul computer.
Sì, oppure...
ma è open office, non è...
Ah, open office.
Ma è sempre funzionato, non capisco. Sì, lui mi si è raccomandato di usare l'HD.
E se crea un PDF?
Sì, vabbè, certo, che è un'assenza di altro. Ma lui no, mi aveva raccomandato di usare l'HD.
Sta venendo?
È a pranzo.
No. Ma non so se bisogna switchare.
Cristiano, ti serve un laptop?
No, mi serve Open Office io. A meno che tu non abbia Linux.
iSource.
Aspetta, dai qua.
Io spegnerei prima tutto e poi dopo luce.
Ma strano perché funziona. Non so, una lezione. Cioè, no, se non ha funzionato non capisco perché. Non so se perché sono io che devo switchare. Ecco, sembra di sì, sì, ci siamo.
Ci siamo. Allora ti dico che abbiamo risolto.
Aspetta un attimo. Ce la fai?
È piccolino.
Okay, let's move on. It's not full screen, but go ahead.
Okay, sorry about these problems. So I'll be talking about the electromagnetic counterpart of this event you've heard already. But before moving to what we learned, what we saw and what we learned from the electromagnetic signal coupled, let's just remind ourselves the story behind these stars, which then finally merged together. So basically, where did they come from and what were they? So just a reminder, first of all, the place, the galaxy they used to be in is a galaxy which is 40 megaparsec away from us, which is 130 million light years away, with a very low star formation rate. So basically, very few stars form nowadays. Well, at the time of the merging, and these stars were once upon a time, which means basically 10 billion years ago. They formed. They began their life as massive stars. So massive, I mean, kind of between 8 and 25, 30 solar masses. So not too massive, but massive enough to explode then as supernovae. And this is just a timeline of their life. Their lifespan basically was within 10 million years. They just completed the fusion of hydrogen to helium and up to iron, and then first one and then the second one just blew off as supernovae. And most of the time here, after they survived the explosion of both components, because sometimes the binary system can be disrupted by supernova explosion, most of the time, which means essentially 10 billion years, they spent their time just as a binary neutron star, which slowly but continuously shrunk, so that because they lost energy through the emission of gravitational waves. Finally, they merged, as we learned, and essentially our story begins here. So you've already heard about the momentous discovery that we saw a gamma ray burst, a short gamma ray burst, just a couple of seconds after the merging. And what I will be focusing on is the electromagnetic signal, through which we learned a wealth of information about this event. In particular, the range, the electromagnetic range, covered 9 decades, from X-rays up to the radio. And what I would like you to keep in mind is the kind of information we obtain from different wavelengths. In particular, from the UV optical near-infrared, we learned a lot about the production of heavy elements and the properties of the host galaxy, while from the extreme wavelengths, which is X-ray and radio, we learned what was going on about the relativistic flow, which was coupled to this merging, particularly the kinetic energy, the density of the medium surrounding the merger, and the geometry of the explosion itself. So this is an important picture which will help you to really understand what I will be saying. And essentially, it's a drawing of we think happened. So you've got two different components, essentially. One which is more isotropic and is dominated by the... we learn about this from the optical and UV and near infrared, while the jetted emission, the relativistic outflow we observe from the jet, we knew from the radio and X-ray. And I will discuss the importance of the line of sight with respect to the system. So how things change when you change line of sight. So how we infer, in particular, the line of sight we observe this event in this particular case. So this is just a time lapse of the discoveries of the incredible number of discoveries within a few hours and days. So I'm not gonna. This has been already covered by the previous talks. I would be skipping. Okay, this is the localization map, which finally allow the optical counterpart search to find the optical candidate. And this is one of the first images, the very first one actually, which was taken 10, 11 hours after the merging, which clearly show on the right you see within 11 hours after the merging, and while on the left you see just a few days afterwards, in which you clearly see that the source coupled with the merging, not only it faded, but it also got red. And this is the first time when Chandra first observed this, he didn't see anything. So also this early non-detection at 2 days after the merging is very significant. So let's go back to the gamma ray burst itself. Before describing the properties, I would like you to keep in mind this. This is a classical scheme which is at the basis of the physical classification that we know as of today of short and long gamma ray burst. These are essentially two families of burst, depending on the most important observable, which is the duration of the burst. So this is the bimodal distribution of the duration. You've got two families, the long and the short. And we knew much more before this event about the progenitor of long burst, which we know they're particular kind of massive stars which already got rid of the hydrogen envelope. And we knew a lot also because we saw many times the associated supernova. No such supernova has ever been associated to short bursts. So before this event, we thought there was circumstantial evidence that short bursts could have been associated to the merging of binary neutron stars. So in this sense, this event represents gave finally us the smoking gun of the association of the fact that short bursts are indeed associated to the merging of binary neutron star. So what about this event? So if here you see the duration distribution I showed you already, and you can see that this event had a duration of about 2 seconds, so lies in between the two classes. But it resembles more typical short burst, but it lies kind of in between. So it's not really a classical short burst. So also here you see another property which I didn't mention is the fact that short bursts are on average harder, spectrally harder than long bursts. And again, this event lies just in between. It's not really as hard as short GRBs typically are. Talking about the released energy in gamma rays and the isotropic luminosity, again, this event is kind of a one-of-a-kind event. This is the first time that we detect such an underluminous GRB. This is just the population of, this line is just the sensitivity line as a function of the distance of redshift. So again, this not only was the nearest short GRB ever detected, but it was also one of the is by far the least luminous one. So by 3 orders of magnitude, less luminous than other previous bursts for which we measured the luminosity. And again, this was possible. We detected it just because it was very nearby, talking about GRB distances. We could have detected it only within a distance of 80 megaparsec, which is twice as far as it was actually. So we detected it just because it was very close to us. So moving on to the X-ray and radio emission that we observed days later. So this is just the typical population of short gamma ray bursts that we see in X-rays. So you see them from the very beginning decaying, and then if you put this event, you immediately see that first you didn't see anything. These are just upper limit from Swift, and this is Chandra, which is more sensitive. So at the beginning, when you first observed 2 days after the merging, you didn't see anything, and then you saw something 2 weeks afterwards, something which was rising. So this is also important to keep in mind. So this is the same plot, and this is the same for the radio band. Again, at the beginning you didn't see anything in the radio, and then finally you began seeing something which was mildly rising. So something that has to be kept in mind when trying to provide an explanation is these features which I summarize here. So the fact that you see a rise in X-ray emission, and then you saw it peaking at around 20, 30 days is still quite uncertain, but not in a very sharp way. So the rise was quite mild. The luminosity itself in X-rays was pretty faint, much fainter by orders of magnitude than typical short bursts are. And also the X-ray spectrum is quite hard, with a spectral index of around 1.5. And also the same index, you get the same index when you try to connect the radio flux and the X-ray flux. This is also very important. So this is just the typical interpretations that have been put forward. So you've got a jet, a relativistic outflow, and in order to explain the faintness, the fact that it's so underluminous, one of the possibilities that you are looking at it from an off-axis angle. And well, there is some kind of dependence also on the structure of the jet itself. Or another possibility is that you are seeing something very faint, much fainter than usual, because you are looking at a more isotropic component, which we believe it's associated to the ultra-relativistic jet, and which is much less relativistic. So Lorentz factor of just a few, and it's more isotropic. So as soon as you are off-axis, you are supposed to see this component, which is much fainter. And another possibility is that you are just seeing either on axis of a jetted emission or just an isotropic emission, which is intrinsically underluminous. So the last possibility I mentioned, if this is possible, if this is the explanation, then how can you explain the rise? The rise, you can only explain it if you think that the peak of the emission coincides with the deceleration of the ejecta, which are shocking the interstellar medium. So the peak time in this case depends on their GOB energy, on the bulk Lorentz factor of the ejector, and on the density of the medium. So measuring the peak, you can measure the bulk Lorentz factor, and you find that it's 2. So it cannot be an ultra-relativistic jet, but it can only be compatible with a kind of cocoon emission. So this much less relativistic, much more isotropic emission, which is thought to be associated. And so we naturally move on to the next one. But in this case, is this compatible with the spectrum we observe? So this is just the spectral energy distribution. This is the radio flux, and this is the X-ray flux. And this is just a number of possibilities. So the one which works is this one, which is not compatible with what you would expect from the afterglow emission of a cocoon. So again, this is not completely ruled out, but makes it a contrived interpretation. And finally, the one which seems to be the most plausible one is that you are just viewing a normal relativistic jet that you normally observe when you see all the other short bursts which I showed you before. In that case, you are looking at the jet on axis, so within the jet. In this case, we see something much fainter just because you are viewing it off axis. So this is just a cartoon showing the game. This is you observing the the jet, you are off-axis. So at the beginning, where this is the Lorentz factor of the blast wave, of the material which has been shocked by the ejector. And this is the beaming, relativistic beaming effect. So as long as the fireball decelerates, the beaming decreases up to the point that you finally see it. So this explains the rise. This explains why you don't see at the very beginning, but just days later. And this allows you to measure the off-axis angle. So this is the game. So putting all the information we got, for example, from the peak time and all this, we constrained the observing angle, so you are off-axis by an angle of 20, 40, 50 degrees. It depends, because there's a lot of degeneracy between the parameters. And using all the data we collected so far in X-ray and radio, up to 40 days after the merger, thanks to using a numerical code which simulates the evolution of this jet through a medium, we were able to constrain the observing angle within a range of 25, as I said, and 50 degrees, and with the released energy in this range, and also we were able also to loosely constrain also the density of the medium. And this was done using a lot of also cluster for simulation, which you see acknowledged here. So this is just for concerning the X-ray and the radio part. Moving to the UV optical near-infrared emission, we learned a lot of other kinds of information that we'll go through now. So what is the kilonova? The kilonova is just a nova which is, the name comes from the fact that it's a theoretical prediction which has a luminosity which is 1,000 times the typical nova. So this just explains the name. But what you expect from this kind of object is just the production of heavy elements due to the decompression of the material. So the nuclei start capturing a lot of neutrons before they beta decay. And so you end up with essentially two families, I would say, depending on the mass number. Below 140, I will be referring to them as light nuclei, and heavy greater than that value. So the essential picture is that you've got two different components depending on the direction. So along the axis, along the angular momentum of the binary, you should expect to see both heavy and light elements with a reasonably high velocity of dynamical origin, while if you look at the system through edge-on, let's say, this way, you should also see, you shouldn't see essentially the light component. You should just see heavy elements produced by the so-called rapid process. And also with an expansion velocity which is still high, 1.1 c, but slower than the other components. See, this was before this event. This was just theory with some possible evidence, but not really as striking as in this case. So again, this is the theory. Depending on the amount of heavy elements are mostly dominated by the so-called lanthanides elements, which are elements whose valence electrons are in the F shells. And this is very important. I will be also commenting later on. So depending on the abundance of the lanthanides, the more lanthanides you have, so for example here the red curve, these elements are characterized by a very large opacity compared to iron elements, iron-like elements. So this turns in higher opacity means a much longer diffusion time. So the object stays bright much longer, and the peak luminosity is smaller. So depending on the abundance of these elements, which are produced by the merging itself, you expect either a blue, quickly fading light curve, or a more red one, long living one. And interestingly, these are the data that have been observed about this event. You see, these are light curves at different filters. This is bluer and this is redder filters. You see immediately that the bluer flux decayed much faster than the red ones. And you can also see the same information here. This has been modeled through the models that I showed you before, necessarily with two components. The blue one, which is a very poor content of lanthanide, and the red one, which is much richer. So essentially, to correctly model the light curves of different filters, you need both components, and the parameters you use to fit is the amount of ejected matter, because the more you have, the more opaque and the medium is, the velocity of the ejector, and the fraction of lanthanide you've got. So two components, the blue one with 0.01 solar masses and but faster expanding, so 0.3 C, and the red one component. This is just by fitting the light curve. So this is a more up-to-date light curve. So you see again the model are just the combination of two components, and this is the same piece of information that you get from the spectra. So this is a spectral evolution. You immediately see at the beginning you've got a strong blue component, which then fades quickly, and then in the end, days later, you just end up with a dominant red component because the blue one has just gone. And this both we clearly saw this effect both in the near-infrared and in the optical spectra. This is a remarkable, for example of how the synthetic spectra, which is the red one, match the observed spectra in the near-infrared. So you see, basically, the basic feature just were really matched, and the matching allowed us to estimate the mass, the ejected mass, the velocity, and the amount of lanthanide in the material. So again, this picture that before this event was concerning the merging of neutron star was more theoretical, just theoretical, has been confirmed to a large extent. And it's interesting to see, well, if gold, platinum were indeed synthesized, where did we see them? And the answer is no, because elements, lanthanide, like for example neodymium, have this feature. They have a huge number of lines, atomic lines, because they are, as I said, their valence electrons are in the F shell, which gives you all this flood of atomic lines, which basically contributes to enhance greatly the opacity and to shifting the flux itself to the near infrared rather than the optical. So the more lanthanide you have, and the more the flux shifts toward the near infrared. And also the ejector velocity is another important ingredient, because we essentially didn't see clearly lines of elements. And this is because you see from the simulations, from these theoretical spectra, should the velocity have been much smaller, for example this value, you should have seen lines. The fact that we didn't see again confirms that the velocity was contributed to blend essentially all the lines into a continuum with some features. So this is the basic picture. The fact that we observe both components constrains also the viewing angle, or the observing angle, which is the same. So we must have seen the event from an angle which is not too far away from the angular momentum or its opposite direction. Not too far means within 45 degrees, let's say. And finally, another interesting aspect of this that this event made possible is also the information we've got. We could derive on the Hubble constant, that was already mentioned. So we know that nowadays that there is this kind of tension between the measure of the Hubble constant you get from cosmic ladders, from type 1a supernovae, and on one side, and from CMB on the other side. So it's significant tension. So essentially LIGO, as was said before, LIGO and VIRGO, sorry, had the capability to constrain the distance and the inclination angle through which we observe the system, but they are degenerate. So there's a mutual dependence on both observables. So using the redshift, you measure the recessional velocity. You could estimate from the fact that the host galaxy belonged to a system from which you know the peculiar velocity. You measure the Hubble expansion. And finally, from the Hubble law, you measure the gravitational waves gives you the distance. You measure the Hubble flow, and then you can estimate the Hubble constant. And this was the value derived from the gravitational waves that was already commented before. What we did is just exploit the fact that the electromagnetic signal allows us to model the jet. But jet means to model the angle of the jet. So through which angle we are observing the system. So we use this information to shrink the uncertainty interval on the angle to exploiting this degeneracy to get some clues to improve the uncertainty on the Hubble constant. So we played this game, and this is what we got. We shifted essentially the estimate of the Hubble constant towards a value which is more toward cosmic ladders estimate rather than to the CMB. But the point is that not just the value itself, it's the proof of concept that with just one event of this exceptional quality, you can just play this game and shrink the uncertainty interval. In this case, the interval shrunk by 5%, so not so relevant. But when you will have, by the time you will have some dozens of this event, you will be in a position to reach % accuracy on H0. What's coming next? Next with this event? Well, it's not over yet, because nowadays, from just 20 days up to now, we couldn't observe it anymore in the X-rays because of sun constraint. The sun didn't allow us to observe, but within a couple of weeks, we will be observing again. So we expect to constrain finally, in a much better way, the properties of this emission, and in particular the geometry and the energy and all these parameters describing both the characteristics of the explosion itself, as well as the interstellar medium surrounding, so the environment of the progenitor. We will be knowing more. We will know whether the off-axis jet is the correct model or not. And also an important point to stress is that one proposed mission to ESA call, which is Theseus, whose principal investigator, Lorenzo Mati, is in the audience here, will be particularly one of the goals will be, for example, the detection of relatively soft X-ray event, in this case also to study the high redshift universe, but just thinking of this very event, this merger, BNS merger event, this is particularly interesting because thanks to the sensitivity and the broadband sensitivity, in particular in the X-rays, it will be capable of detecting this transient, very weak event. So enhancing the number of electromagnetic counterpart to nearby, relatively nearby black hole, neutron-star mergers. And so this will give presumably great input and great increase, will contribute to increasing greatly the number of such events. And just let me end this way, just reminding ourselves that how Einstein predicted in this very first article that essentially gravitational waves have the same velocity as light. And this is nice to remind, I guess, with his very own words. That is it. Thank you.
Thanks, Cristiano. Beautiful wrap up on the afterglow of science. Questions?
Thank you. One of the experts you talked was about the fact that you were almost able to predict how much matter was emitted on axis and off axis in total of mass. So you have a real prediction, the value that is off axis, very relativistic one, 0.03 solar mass, and 0.1 on the equatorial plane. Is that correct, my interpretation?
No, I think it's the other way around.
Okay.
You've got 0.04 solar masses in the red component. So essentially, we observe everything from just one angle. So what I can tell you is the amount of mass in both components. So the one lanthanide rich and lanthanide poor, because they have different behavior in time. So just both fit in the multi-filter light curves on one side, and also trying to match the spectra, the observed optical and near-infrared spectra, with the templates just produced by models. You end up essentially with the same estimates of masses, objective masses, and velocities. So for the blue component, you have 0.1, 10 to minus 2, 10 to minus 2.
That would be on axis, no?
Yes, that we are expected to see that component only if you are not too far away from the binary axis. So that's why. Otherwise, we shouldn't have seen it. That's the point. Because otherwise, you have to go through the cloud of lanthanides rich material, which essentially moves all the peak that you would observe in the blue filter, it shifted down to the near infrared. So the fact that we saw that short-lived blue component means that we cannot be too far away from the axis. So I don't know if I answered.
No, the point is that is one of the things one want to check with numerical simulation, how much matter is expelled on the equatorial plane with respect to the one in the direction of the axis. And so that could give a clue which is the principal mechanism for the ejection of matter. And
yes, I think that we need to know, we will know more about that as soon as we will have observed many events with different angles. This is just one case. So what we would have observed should the angle, the observing angle be much closer to 90 degrees, who knows? So we just know one part of the story. So I guess to have a definitive answer, we should collect more events. That's what I believe.
Something that certainly I suspect was quite a surprise is that a lot of mass anyway was ejected. In the sense that, isn't it, Roberto, in a lot of simulations, the typical amount of ejected matter was quite significantly smaller. And maybe I'm wrong, but it seems to me that there is some sort of, with Giuseppe we like to call it tension, in a sense, almost tension maybe, in the sense that you needed to eject a lot of mass dynamically before or during the moment of a merger, but also apparently you need to eject a lot of mass after from this object that has not yet collapsed into a black hole. So from one side, you need to be in the condition to have a lot of dynamically ejected, shocked ejected mass, but at the same time, the system, the object that you have formed, need to live long enough so that after you can eject this, I don't call 0.04 solar masses. And these two things, in a sense, they are almost pointing, interestingly for us, in the opposite direction. Because if you want to have a lot of mass ejected after, the object needs to live relatively long. And that puts certain constraints, for instance, on the mass radius, blah, 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 blah. And if you want to have a lot of mass ejected before, then, for instance, typically you need to have the collapsing object with small radii, and that, in a sense, goes in the opposite direction. So, of course, as you said, I mean, the data is the first event, but it's interesting because if this trend would be confirmed, would help in understanding what happens before and after the merger to the equational state. I don't know if you share. I mean, is it okay what I said? I mean that it was a little bit of a surprise that all this mass was ejected, and in any case, the mass is apparently ejected with two quite different mechanisms. Is it correct what I said?
Yes. From what I saw, from what I read, yes, I would say it can be taken as a marginal possible evidence of these mechanisms, as you say. Yes.
Yeah, Cristiano, I have a couple of questions about the Hubble constant. So first one is, I mean, the error bars now are quite large. So how long? When can we expect a, 2-3% measurement of the Hubble constant?
Yeah, we ran some simulations. We should collect some kind of 50 events. Yes, 50 events to reach percentage accuracy. But again, I mean, events like this are quite remarkable, just because you see that it depends also. There is also dependence, as was mentioned before, also on the angle, because well, there's another point that I should have mentioned before, and I tell it now. This event was quite remarkable in the sense that it was very close. So I don't know how much this will be representative of the future events. Yes, it was a very lucky one. And this is particularly relevant for the game we played by combining the gravitational wave and the electromagnetic, because we finally detected the X-ray in the radio afterglow, because we kept observing it, and we finally got it with the most sensitive detectors we have now, which is Chandra for X-rays and the VLA. So if you put the very same event just a little bit further, okay, you'll still see in the gamma rays, provided that you go not beyond 80 megaparsec. But then, if you move further, you just see the gravitational wave, but with the current telescopes, both X-rays and the radio, you won't be able to see the electromagnetic counterpart. So this, of course, is against just the possibility of extending on a routine basis this game. But yes, I would say from the simulations we run 50 events, you should combine 50 events to reach that accuracy, I would say.
Okay, thanks.
Just wait the microphone.
Concerning this argument, so there was a very lucky coincidence. One gravitational wave signal, one gamma ray burst. And the prediction were one gamma ray burst for every 1,000 of gravitational wave signals. So this means that either gamma ray bursts are isotropic, either we are seeing it off axis. And there is a correlation, of course, of the chance probability between the jet opening angle and the distance. So if this is a typical gamma ray burst, short gamma ray burst has cosmological ones with 5-10 degrees collimation angle, it is clear that if you put it very close, the co-moving volume subtended by this angle is very small, so it is very likely to see it off axis. Instead, if you put it at a distance which is larger, you will have much more probabilities of detecting it on axis or less off axis, let's say. So I would not. So for me, this argument pushes a lot towards being a collimated, classical collimated gamma ray burst seen off axis. This pushes me to not be so pessimistic, because this is maybe a very typical short gamma ray burst. And if instead at 40 megaparsec it was at 80 megaparsec, the chance probability of detecting it would increase to detect it more on axis, no? So its apparent luminosity, the gamma rays, the X-rays, and so on, will be higher. So if you take this kind of events and you move them to higher distances, for a paradox, you may see them.
Because the so-called Malmquist bias. But the point is that if you look at this problem from the gravitational wave point of view, you see that most of the events that you do see in gravitational waves, you will be missing them in the electromagnetic, because you keep seeing them just regardless of the observing angle. But that's crucial for the game of observing the afterglow in the electromagnetic bands, because if you are not on axis, as you say, you are not going to see it. So the number of gravitational events without an electromagnetic counterpart, in terms of the afterglow, I mean, increase as long as you move further out.
There is
because you keep seeing in the gravitational wave, you keep seeing regardless of the angle. But this is crucial instead for the afterglow detection.
There is a partial compensation, but this the co-moving volumes that is subtended by the jet opening angles. Anyway, yes.
Yes, of course. You see much more
gamma ray bursts are likely to be detected less off axis, so with a higher luminosity. Okay. Right. Yes.
Yeah, but it's the same game as we used to see with the long gamma ray burst, essentially.
Cristiano, this is just a comment concerning Theseus.
Yes.
If you can show, I would like to stress the importance of Theseus. Here we have the PI of this proposed mission. In the case of the discovered gamma ray burst, and then of the micronova, the association between gamma ray burst and the gravitational event is not positional, but is all temporal coincidence. On the basis of the temporal coincidence, we have identified the gamma ray burst with the gravitational wave event, and then the identification, the association of the macronova to the same event, correct? In this case. But this, you know, the error box is about 31 degrees, square degrees, and is very large for the discovery of an optical counterpart. You take into account that, for example, in the case of Bazzi, that provided the gamma ray burst with an accuracy of a few degrees, was not possible to discover an optical counterpart. In the case of Theseus is very important because it has a very wide, broad field of view, more than 1 steradian, and at the same time is capable to localize the event, the gamma ray burst, with an accuracy less than 1 arc minute. Could be also 30 arc second. This is very important because the temporal coincidence is obviously a strong argument to identify the event, the gravitational event, with the gamma ray burst event. But I want to recall you, for example, that in the case of Beppo-Sachs, when we started the search of something after the event, we discovered in 97-11 January 11, we discovered an event we gave the localization uncertainty. The error box was, I don't know, around 3-4 arc minutes, 3-4 arc minutes. And we discovered in this region, we discovered a radio source which faded very rapidly. Never was observed a radio source with this very fast fading.
Yeah,
After 1 week, we reanalyzed the error box, and before saying this one, once we have discovered this radio source, we submitted a paper to Nature. The paper was accepted, but after, 2 weeks, we reanalyzed the error box of the Wi-Fi camera, and in this new error box, the source was no more inside.
If I make a couple of comments on what you said.
So this what I mean is important.
That's crucial. The capability of properly localizing the X-ray counterpart down to 1 arc minute is absolutely crucial. I have also to remark that on one side, from the Bepo-Sax era, things have moved on, so that nowadays there are optical surveys which automatically can detect out of 10,000 events, candidate transit events, they can quite reliably detect the optical counterpart associated with it. But this is not enough, I absolutely agree, because it took 11 hours to get the right one. And this was an easy task, because it was a very bright optical counterpart. So in the future, when we will be expected to have a much more challenging optical counterpart, it's going to be even more time-consuming and more challenging. So having the capability of promptly and accurately localizing the X-rays is absolutely crucial. But on the other side, the optical surveys are much more well-equipped nowadays, and so they are also orders of magnitude more ready to deal with this challenge than it used to be in the Bepo-Sax era.
Okay, so thanks again, Cristiano. We can go to lunch. I think there were 25 lunches ordered, or at least that was the order. So I think we are a factor of 2